So here, B, B part 1. State the origin of the centripetal force calculated in A part 2. So just now on the first page, we already count the centripetal force. Now we want to understand where is the centripetal force come from. So you know centripetal force is the resultant force that acts towards the center of the circle. That is what we learned from the first chapter. That's the resultant force. So what force is acting over here is actually the gravitational force. It's actually the gravitational force. Okay, so state the origin of the centripetal force. So you can say it is because of the gravity. So you try to understand that as long as the sun and the earth have masses, then they will attract each other. They will attract each other, and that attraction force provide the centripetal force. So that is the concept that we have to take now. Okay, now part 2. Determine the mass of the sun. Okay, determine the mass of the sun. So we have to use that concept again. The gravitational force provides the centripetal force. So we already count centripetal force from A part 2, which is 3.46978 times 10 to the power of 22. This is what we count previously. And for the gravitational force, we can use Newton's law of gravitation, which is Gmm over r squared. So we can use that formula. So G is 6.67 times 10 to the power of negative 11. Mass of the sun we don't know. Mass of the earth we know. 6.0 times 10 to the power of 24. And then at the bottom we have to put the r. R is the distance between the sun and the earth. This is also given 1.5 times 10 to the power of 11 square. And then we'll get the m by just moving around the values. Then you will get m as 1.95 times 10 to the power of 30. That is the mass of the sun. Okay, so the very important concept here is gravitational force is equal to centripetal force. So remember that, and everything will just work accordingly. Okay, so we move on. 2.3. Gravitational field strength again. Okay, gravitational field strength. So just now I already explained this is G. So this is G. Gravitational field strength is G. So the gravitational field strength at a point is the gravitational force exerted per unit mass. So from here, you will realize that they are trying to say that gravitational field strength is equal to gravitational force divided by mass. So your gravitational force is Gmm over r squared. Then you divide by m, right? Then you can cut the m, right? And then you will get Gm over r squared. So you will get the gravitational field strength. Okay, so let's see here. They are trying to derive it in different way. So this is where I derive it based on the definition given. Okay, so this is another way. By equating W equal to mg and Newton's law of gravitation. So this is the gravitational force equal to mg, Yeah? Then you can cut the m on both sides. Then you can get G equal to Gm over R square. Gm over R square. Okay, now let's say I give you one example on how we apply this on our questions. Okay, so let's say for example, okay, I put two objects. One is the Earth, another one is the Moon. Okay, so in this case, if we apply this formula, okay, if you apply this formula, right, then you get the G. Okay, you get the G. The thing is, are you getting the G on the Earth or are you getting the G on the Moon? You know, the G on the Earth and the G on the Moon is different. The G on the Earth is 9.81 and the G on the Moon is smaller. So if you apply this formula, are you getting the G on the Moon or the G on the Earth? We have to clarify that. Okay, so let's put it in this way, no? Let's put it in this way. So let's say the mass of the Earth is capital M, the mass of the Moon is small m, small m, okay, small m. Okay, now what to do is the distance between the Earth and the Moon is r, Okay, so you are dividing. You are dividing by the mass of the Moon. So based on this working, you are dividing by the mass of the Moon, and then you get this. Okay, so then the thing is, this G is G on the Earth or G on the Moon. We have to know about that. Okay, so to know about this, right, we can put it in this way. So mg equal to gmm over r squared. This is another way to derive it based on the notes. So if I'm using small m, right? So you need to know that this is the mass of the Moon. This is the mass of the Moon. And then how about this G? So you need to know that this G is actually the G of the Earth. The G of the Earth. Okay. Why is it like that? You imagine. Let's come back to something which is simple. Let's say something that we learned before. You stand on the Earth. Okay. Your weight is mg. W equal to mg. So the m is the mass of the human. The g is the G of the Earth. 9.81. So when you extend your concept here to this situation, the m is the mass of the Moon, the g is G of the Earth. Okay, so that means when you do it in this way, right, you cut the m away. At the end, what G are you counting? You're counting the G of the Earth. You're counting the G of the big M. In other words, you're counting the G of the big M, which means the G of the Earth. So you are counting the G of the Earth. Huh? So if you want to count the G of the Moon, then how? So of course you have to do it in the other way around, right? You divide by the capital M, divide by the capital M. So okay, I put it in this way. G equal to Fg divided by capital M, then you get Gmm over R square over M. And then you cut the capital M away, then you get Gm over R square. And then this is the G of the Moon. Okay, so this is the G of the Earth. Okay, so you have to know that. The top one is the gravitational field strength of the Moon. Of the Moon. You follow the M here. If this is small m, then it's the Moon. Okay, if here is the capital M, then this is the G, the gravitational field strength of the Earth. So be careful. It's a bit confusing, but be careful. Okay, be careful with this thing. Now, let's move on first. Okay, so why I have to put so much detail here, because past year question they asked before. So some people are confused and they need clarification. So I have to put it here to let you know about that. Okay, now let's move on. 2.4. So 2.4 is about gravitational potential. Gravitational potential. So what is that? This is actually phi. Phi. Okay, phi. So gravitational potential, the symbol is phi. And what is gravitational potential? The gravitational potential at a point is work done per unit mass in bringing a mass from infinity to the point. To the point. Okay. To the point. What point are they talking about? We have to clarify that also. Okay. What point? Okay. So let's say example. Okay. Let's say this is the point that we are talking about. Let's say this is the point that we are talking about. This point. So you want to count the gravitational potential at this point, right? Then you need to find out the work done per unit mass. Okay, work done per unit mass to bring the mass from infinity, from a place which is very far away, to this point. Okay, how much work is done from very far away to this point, and then that work done per unit mass is equal to the gravitational potential. So, okay, kind of complicated. You have to know. You have to know that gravitational potential is work done per unit mass. Okay. Now, let's move on. Formula: gravitational potential equal to minus gm over r. Minus gm over r. So that explain why there is a minus there. So you can see here, the negative sign is because gravitational force is always attractive. It's always attractive. So this is the reasons why there is a negative. Then maybe you're wondering, this one. I mean the first page. Fg, the gravitational force equal to gmm over r squared. But this formula has no negative. And gravitational force is attractive also. Why these are no negative and here we have to put negative? So in fact, this formula supposed to have negative also. We just ignore it because we want to make it easier. supposed to have negative. So we just ignore the negative to make the calculation easier. But this one, we can't ignore it anymore because the negative is very important here. It means a lot here. Okay, it means a lot. So now they are trying to explain why you can't even ignore it at all, so we have to put it there. Okay, so first, because it's attractive. Second, because gravitational potential reduces to zero at infinity. Reduces to zero at infinity. So it means that it means something like this. With the graph is like this. Phi versus r. So it's like this. That negative is important because if there is no negative, right, our graph will be like this. Without negative, our graph will be like this. Okay, so that's why we need a negative to fulfill some theory. Okay, some theory. What kind of theory? Let's say. Okay, so I label it first. I have two graphs here. The graph on the right is phi equal to minus gm over r. So without negative, the graph will be like that, and something wrong with the graph already. Without negative, something wrong. Something wrong. Okay, what's wrong? Let's see the explanation here. They said gravitational, okay, the second point, gravitational potential reduces to zero at infinity. Okay, so this is common sense, when the object is very, very far away from this, there is no attraction from each other, So when there is no attraction from each other, then the gravitational potential should be zero, should be zero when they are very far away. So very far away should be zero. Very far away should be zero. And okay, that is not enough to explain why we have to put a negative. Let's see some more. Gravitational potential decreases in direction of field. Decreases in directions of field. So that means what? That means we need a negative. We need a negative so that when you bring the object from very far away from infinity and put it nearer and nearer to this object, the gravitational potential decreases. We want it to decrease. Okay, we want it to decrease. Okay? So the only way to make it decrease is when your formula has a negative. If your formula has no negative, right, it will increase. It will increase when you bring a unit mass from a far place and go nearer and nearer to the earth, let's say to the earth, then it will increase. Without negative, it increase. So we don't want it to increase, we want it to decrease. So the only way to make it decrease is with a negative. Then it will decrease. Okay, from zero and decrease. So it works with a negative. So this negative cannot be ignored because of our situation here. Okay, we want it to decrease. Okay, so let's move on. Next part. Okay. On Earth's surface, we can use the equation gravitational potential energy equal to mgh. This formula is true for Earth's surface only. However, this is not true for masses from far from Earth's surface because we assume g is constant. So this formula, you use g equal to 9.81, right? So then you can use the formula. But in if you go beyond of Earth's surface, we can't, because g is not always 9.81. G is changing. It's changing. Okay, so that's why we can't do that. And next point, gravitational potential energy. So gravitational potential energy of a mass m at a point in the gravitational field of another mass m is the work done in bringing that mass m from infinity to that point. So you will feel like gravitational potential energy is work done, gravitational potential is also work done. Then what is the difference between gravitational potential energy and gravitational potential? So we need to know it clearly. Okay, so first of all, the symbol that we use is different. This one we use U. Gravitational potential energy we use U. And just now the gravitational potential we use phi. Okay. There is a small difference between these two. The difference is gravitational potential is work done per unit mass. Work done per unit mass. Per unit mass means per kg lah, no? Per kg. So that means how much joule is used to bring 1 kg from very far away to a particular point. That is gravitational potential. Okay, how much joule, work done means in joule, right? So how much joule is used to bring a 1 kg mass from infinity to a particular point? That is gravitational potential. But gravitational potential energy, right, it is not limited to 1 kg. Okay, it is any mass. Okay, an object of any mass. So, and it is, let's say you have an object, asteroid lah, let's say asteroid. So you want to bring, okay, let's say a stone. You have a stone of a particular mass. You want to bring it from infinity to this point. Then the joule that involved is gravitational potential energy. So the difference is how you put the mass on it. Is if it's 1 kg, gravitational potential. If it's any mass, then gravitational potential energy. So the formula is slightly different also. Slightly different. We just have mass here. Okay, we have mass there. M phi. You can see the formula, M phi. M phi. U equal to M phi. That means you take the gravitational potential, you multiply with M. What M is that? This M is the M of the object. Let's say the stone just now. The stone that you are going to bring it to this point. That stone have mass M. That M is substitute here. Is the one that you are planning to bring it near to the point. Then you put it here. And then this capital M, of course, is the capital M of this one, the one that is not moving. The small m is the one that you plan to bring it near to the capital M. Okay, so then the phi, right? You can see here the phi is where they replace with the formula up there. So this formula, they substitute at the bottom here, then you get this, and you get the gravitational potential energy. Okay, now next point. So you can see here the gravitational potential energy difference between 2 points is the work done in moving a mass from one point to another. So that means what? That means it's not from infinity to a point anymore. It is from one point to another point. One point to another point. It's not infinity to this point. It is just 2 points that are not infinity. So you want to find the work done from one point to another point. So the work done here is the gravitational potential energy difference. And how to do it? You take the m5 final minus m5 initial. Okay, m5 final minus m5 initial. Okay. Example, let's say you are bringing an object from this point to this point. So this point is called m5, or this point is where you can work out your m5 initial. And this point is where you can work out your m5 final. M5 final. Okay. I give you a few situations here. Let's say I draw out two diagrams. So first diagram, okay, you have capital M here. So you bring a stone from this point to this point. Okay. So then how to count the gravitational potential energy? This is example one. Example one. Another example that I'm going to give here is you still have the capital M. Let's say this is the Earth. Now you are going to bring the stone away from the Earth. Okay, so this is example two. So I put two examples, and you try to imagine on how we count the gravitational potential energy. So the first point, let's work out the R first. Let's say this is the R final. This is the R initial. Initially the stone is here, then you bring it to this point. So this is the final R. This is the initial R. Okay, so you can see a situation like this. Delta U equal to M phi final minus M phi initial. Then phi is minus GM over R, right? So minus GM over R final minus GM over R initial. Okay, so simplify it. Minus GM M over R final plus GM over R initial. Okay. What am I planning to let you see is I want you to predict this is going to be a negative value or a positive value. So imagine RF is small, RI is big. So RF is small, RI is big. So you have to imagine whether you will get a positive answer or negative answer in this case. So if Ri is, okay, I use blue color now. If Ri is big, then this whole fraction will be small. If Rf is small, then this whole fraction will be big. Okay, so what am I trying to say is a small positive value minus with a big value, so you will get negative. you get negative. You get negative. Okay, you get negative. So I write down the main idea that I'm trying to say here. When you move n towards m, so your delta u is negative. It's negative. So example 2 is just the other way around. The other way around. You are moving the stone away from the earth. So initially it is small, and at the end it is big. So everything will be the other way around. Okay, so conclusion, move m away from m. So your delta u will be a positive value. So that is what am I trying to say. It will be a positive value. Okay, so we have done everything here, and now let's look at past year question.